So in this short talk, I'll be discussing about some of the key ideas behind the proof of Fermat's last theorem. So I'll begin with the following question. So we have the following equation: x square plus y square is equal to z square. And the question said that whether there is any non-trivial integral solution to this equation. And by non-trivial, I mean that I am not allowing any of the variable to take value 0. And the answer turns out to be yes. Like you can take x to be 3, 4 and 5 like x, y, z, and they will satisfy this equation. In fact, they will form a right angle triangle, and then Pythagoras theorem tells you that they will satisfy. In fact, we know all of the solution of this equation that can be classified using this type of parameterization. And one of the easy way to get this parameterization is to transform our original problem to a geometric problem. So we'll divide by z square both sides, and then we will get the following circle, unit circle, and then our problem change into finding rational points on this unit circle. So this is how we will find it. So we will fix one rational points on the circle. You can fix any. Here I have fixed 0, -1, and then you construct all the lines going via this point with rational slopes, and they will intersect the circle at some point, and in this way you will get all such solution that were in the previous slide. So now if I ask the same question with the exponent n greater than or equal to 3, then in that case the answer turns out to be no, and the reason is Fermat's last theorem that was proposed by Fermat in 1637 in one of his notebook, where he claimed to have a marvelous proof of this theorem, but he said that he don't have enough space to write it, and in margin of his notebook, So, and it took mathematical community almost 250 years to solve this problem. So it says that there is no non-trivial integral solution to the equation x power n plus y power n is equal to z power n for n greater than or equal to 3. So let me give a quick outline of the proof. So the proof go via some contrapositive argument. So suppose this equation has a non-trivial solution, call it ABC. Then what we will do, so we will associate certain geometric object called elliptic curve to this solution ABC. So I will come later what does that elliptic curve mean. So then in 1986, Kenneth Ribet proved that if such elliptic curve exists, then they can't be modular. So in my later part I will define what does modularity mean. So for this time you can just assume it. And then in 1994, Unraveling proved that a certain class of elliptic curve is modular, and that class contains elliptic curve which we were assigning to the solution of the Fermat's equation. So it contradicts Ribet's theorem, and hence such a solution cannot exist. So this is how the proof of Fermat's last theorem goes. So let me start with defining elliptic curve. So an elliptic curve is a set of rational roots of a cubic polynomial which have this form y square is equal to x cube plus ax plus b, where a and b are integer, and in addition to this we need some smoothness condition. And why these elliptic curves are important? Because of two important aspects. So the first one is they are geometric objects because they are cubic curves, and the other thing which is most important is they have an algebraic structure. So what structure they have? So this is how a typical elliptic curve look like in xy plane. So this is y square is equal to x cube minus x. So if I have to define an operation on it to make it an algebraic group, so we take 2 points, say P and Q. We will draw a straight line going via P and Q, and since it's a cubic curve, it will intersect it somewhere, and we will take its reflection and then call it its sum of P and Q. We will call it P plus Q. And what if I want to add one point to itself? So in that case I will draw a tangent at Q, and then again I will do the reflection, and that is Q plus Q. So this is how we define addition on this, and one can verify that with respect to this addition they forms an abelian group. So I will not go into detail what is the identity here because I don't have enough time. So let's go to so one of the natural question that Diophantine and arithmetic geometers study is when an elliptic curve have some rational points. So this problem is not very easy because there are elliptic curves which have finitely many rational points. Some of them have infinitely many, and there are which have none at all. So one of the way to study elliptic curve is to reduce them on some nice field. So suppose this was our elliptic curve with integer coefficient. So we will reduce it to a finite field. So suppose Fp is a field of P element, and this here A and B are reduction modulo P. So now we have our elliptic curve defined over a finite field. And if you remember, there was some smoothness condition in the definition of elliptic curve. So from that, this EP will not be elliptic curve for all prime. There will be few bad primes for which this smoothness condition will not satisfy, but they are only finitely many. So that's not a problem. And the good thing about reduced elliptic curve is because they are defined over finite field, so we can count point over that. So that gives rise to certain Dirichlet L function. So for this elliptic curve E over Q, we have reduced it on some finite field. So that will give rise to some L function which is defined using this Euler product. So if you see this AP here is related to the number of points on elliptic curve on that in that field, and this 0, 1 depend on whether my P is a bad prime or good prime that I had discussed in the previous slide. And you can recall that how we define a L function using Euler product. So it is the similar process. So next course of action is to define modularity. So for that I have to introduce modular form. So modular form are analytic function on complex upper half plane, which are in some sense generalization of periodic function with some additional symmetry, which is given here. So the periodicity of f implies the Fourier series expansion of f, and that gives rise to this series, Fourier series. And if we write in this Q expansion, so we have this sequence Bn here. So once we have a sequence here, we can again attach an L function to it. So that gives rise to an L function attached to a modular form, which is defined using the Fourier coefficient of the modular form. So now let's come to the connection of elliptic curves and modular form. So an elliptic curve E is said to be modular if there exists some modular form f such that the L function of elliptic curve matches with the L function of that modular form. So this is how we say that an elliptic curve is modular or not. So there was a famous conjecture due to Taniyama and Shimura, which was proposed in 1957, which says that all the elliptic curves over Q are modular. And Andrew Weiss actually proved a very special case of Taniyama-Shimura conjecture, which is that all the semi-stable elliptic curves E over Q are modular. And as a corollary of that, he got the proof of Fermat's last theorem. And a small remark here is that this Taniyama-Shimura conjecture is now a theorem due to Breuil, Conrad, Diamond, and Taylor in 2001. So they have solved it for all the cases. So if you are still with me, then you can see that we have associated a elliptic curve to the solution of Fermat's last question. So these elliptic curves are semi-stable, and Ribert's theorem tells that if this AB are coming from solution of Fermat's equation, then this EP can't be modular. But as you have seen in the previous slide, Weil's theorem, that semi-stable elliptic curves over Q are modular, so that contradicted. Hence, such a solution cannot exist. So that's the proof of Fermat's last theorem due to Andrew Weil's. Yeah. So here is Andrew Weil's announcing his proof of Fermat's last theorem. Yeah. Thanks. That's it.
So we have time for a couple of questions.
Is there a chance that you have a simpler proof that I can understand?
Maybe. So there is a mathematical community. So like Fermat himself said that he has a marvelous proof. So no, but that Fermat's proof never appeared, right? So people might think there might be some other way to prove this that Fermat was thinking. That might be simpler, but we don't know. Yeah.
No, in connection with what Professor Bhaskaran is saying, I was recently reading a book which shows that Fermat himself realized the mistake, because there is in his notes, he's basically working out this thing and he realizes a mistake. So that's why he actually never published anything. So he himself knew that the proof he had in mind was wrong, and he never felt the need to erase it because it was anyway only for his private thing. Yeah. It's just chance that we happened to read it. Any other question?
On this thing, x cube plus y cube is exactly plus or minus 1. it has infinite number of solutions.
Can you repeat the equation?
X cube plus y cube is equal.
Yeah.
X cube plus y cube is equal to z cube plus or minus 1.
Okay.
So that seems to have, just adding 1
Yeah.
seems to have enormous number of solutions,
Yeah.
and Ramanujan himself has worked out. Is it easy to see from the elliptic curve kind of?
So the here that we have the Fermat equation x power n plus y power n equals z power n. So in that case, it's very easy to get some nice elliptic curve for which we have this modularity condition. So like as you said, we can add plus minus 1, but in that case we might get some curve, but for that the proof of modularity theorem might be very difficult. So this type of, I don't know if this type of idea will work there. So here the curve we have, they falls in the category of phrase curve. So for them we know modularity theorem and all these things. So